Thank you. Oh, yeah.
It's a great pleasure for me that Arlene Kim is back from Korea come to this Newton program. Arlene was my former postdoc. She did a PhD in Yale with Harry Zhou, and she's going to speak today about adaptation in log-concave density.
Thank you, Richard. So thank you for coming to my talk. So today I'm going to talk about adaptation in log-concave density estimation. This talk is based on the paper which is recently accepted and also ongoing work with Oliver Feng, who is a PhD student, and Richard, and Aditya, who is the assistant professor at Berkeley, and Richard. This is the outline of my talk. So first, I'll give you some overview of log-concave density estimation, and then I'll move on to the additive property, which is the main topic of this talk. For the univariate case first, and then I'll move to the additive property of our estimator for the multivariate case for dimension up to 3. And then I'll talk about a little bit more research where the dimension is more than or equal to 4. The area in shape constraint estimation was pioneered by Grenander, who considered estimating a decreasing density on 0 to infinity. So he proved that the maximum likelihood estimator for a decreasing density is the same as the left derivative of the least concave measurement of this empirical distribution function. So this part is empirical distribution function, and you consider the smallest concave function outside of this empirical distribution function, then this is piecewise linear concave function, which has some kings here, here, here. So if you take the derivative of that function, basically you will get the piecewise linear function, because that's the same as the slope of this piecewise linear function. So that's the MLE. And Grenander found this is equal to the maximum likelihood estimator, and we call it as Grenander estimator. So since then, people have considered many other type of shapes like concavity, convexity, monotonicity, and low concavity, and so on. And also there has been a lot of recent progress because of the development in empirical process theory. And in this area, we want to take advantage of the shape in the statistical estimation. So in this talk, I assume that the density is log concave. And first, we need to know what concavity means. I'm sure everyone knows this. So this concave, this is the actually definition in the actual computer. And saying having a linear surface that curves inwards like the interior of a circle or sphere. These functions are all concave functions. And the log concavity, the definition is quite simple here. So we say f is log concave if log of f is a concave function on its domain. So we can write down f is like exponential of concave function phi. As you can see, many parametric densities satisfy log concavity. Think about this normal, whose density is like exponential minus x squared over 2. And if you take the log for that normal function, that's minus half x squared, right? So that's a concave function. And all the other densities like logistic, Laplace, all the other densities are all log concave. So these are some examples on the univariate log-concave densities. In addition, this class of log-concave densities satisfy a lot of good properties, which are the properties of normal class. For instance, all log-concave densities are unimodal, so it has only one mode. And log-concave densities have convex level sets. So if you chop the density horizontally, then the cross-section parietal or concave set. And lastly, if we have low concave density, if you take the marginalization, then the resulting one is low concave. So that's the property of closeness under marginalization. Also, conditioning and convolution operations under these operations, we have the resulting one is also low concave. So these properties are very similar to the properties of normal density. So we can think of the class of low concave densities is a natural generalization of normal to a non-parametric class of densities. So this class is non-parametric, definitely, but with these good properties. Generally speaking, non-parametric class doesn't guarantee the existence of the maximum likelihood estimator, but in this case, we can show that there exists a unique maximum likelihood estimator. So for this talk, we suppose that we have IID sample from the true density of 0. And then we consider our estimator, which is log-concave MLE. And this estimator FN hat maximizes the log likelihood function over the class of all log-concave densities. So the unique existence is guaranteed for this class of densities. And actually we have R package to calculate this log-concave MLE. And that's the example of bivariate log-concave density and log-concave MLE. I think I use a true density as normal, and I got like 100 observations from normal, and I put in the package, R package, and calculated MLE, and R calculates MLE. This is a shape of the log-concave MLE shape. And here, I'm interested in the accuracy of this log-concave MLE estimator, ML estimator. I want to know that this estimator is very good estimator for the true density of 0. So I'm wondering how accurate is FN, the MLE, as an estimator for the true density of 0. So in order to think about this question, we need to somehow measure the difference between FN hat and F0. And in order to do that, we need to think about the loss functions. And there are many different loss functions. And in this talk, mainly we are considering these 4 kinds. The first one is total variation distance, TTV. This is half times of the L1 distance between FN hat and F0. The second one is squared Hellinger distance, and this is the L2 norm between square root of density. These two, number 1 and number 2, these two are bounded. Total variation distance is bounded above by 1, below by 0, and squared Hellinger is bounded above by 2 and below by 0, because these functions, FN hat and F0, are all density. Third one is Kullback-Leibler divergence, which is defined as integral FN hat log FN hat over 0. As you can see, this is log ratio, so this is not bounded. The final one is called KL, Kullback-Leibler data. So this is close to Kullback-Leibler divergence, but we replace this FN hat with the empirical part. So this is the log ratio. We took a log ratio and then we take the average at the data points. Okay, since there are really many different possibilities, but in fact, there are natural orderings between these loss functions. We know that squared total variation distance is smaller than or equal to squared Hellinger, smaller than or equal to KL, and smaller than or equal to KL at data. And KL at data, we write it as dx squared. The first two inequalities are quite standard. You can find it in the textbook, basically, the proof of these two. And the third one relies on the fact that Fn hat is the MLE. Okay, so although there are so many different choices, if we have an upper bound result for the last one, then all the three cases are kind of automatically obtained. On the other hand, if we have some sort of lower bound for the first loss function result, then we will have automatically the lower bound for the other three cases. So this is very convenient. But yeah, we need to think, we need to be careful when we use KL or dx squared because this can be unbounded, as I said before. And there are some previous works on these accuracy results for the log-concave MLE Fn hat. In 2007, Pell, Woodruff, and Meyer proved the consistency on the Hellinger distance. And then the multivariate version was proved by Q and Samworth. Convergence rate under the x squared loss function was obtained by Doss and Werner, where the rate was n to the minus 4/5. This is the result, this is the univariate result. And then me and Richard, we took a minimax approach. What we proved is the supremum risk, the Hellinger risk, can be upper bounded by n to the minus 4/5 when dimension is equal to 1, and n to the minus 2 over d plus 1 when d is equal to 2 and 3. So I wrote down this way because it's compact, but actually the first one is larger when d is equal to 1, and the second term is larger when d is equal to 2 and 3.
I think I said this before, that's not quite right? The lower bound is n to the minus 2 over d plus 1, more dimensions. We don't have this upper bound.
So I thought this is only for d less than or equal to 3, and minimax lower bound for all d. Yes. Yeah, so this result was obtained only for the dimension less than or equal to 3. But yeah, the minimax lower bound, we proved this is also minimax lower bound for all dimensions. Yeah, so if we find these rates for the upper and the lower matching for dimension less than or equal to 3, basically in a minimax sense, this problem is kind of solved up to d equals to 3. Because we found the optimal rate, we had the lower bound and upper bound together, the matching bound. But this minimax criterion only considers the worst case scenario, because we take the supremum of F0. So this one only think about the F0 is really difficult case. So we thought that maybe there exists some sort of density. If the density is quite easy to be estimated, then maybe without this supremum for fixed F0, we will have a faster rate of convergence of our log-concave MLE. So we wanted to know whether it's possible to get a class of densities which shows a better accuracy than this minimax optimal rate. So that's how we start to think about this adaptation property. So the idea is this. So we know that our estimator at Van hat, if we take the log of log-concave MLE is a piecewise affine concave function when dimension is equal to 1. Here I draw some plots. This blue curve is the log of the true density. So I use the normal density in this case as well. This is log of our true density. And from this truth, we obtain the sample of size 50. And I drew it with the red dots here. And with this sample, we can calculate the log-concave MLE with our package. And then I took the log of that log-concave MLE and plot it here, which is piecewise affine concave function. Since we know that this log of Van hat is a piecewise affine concave function, we can expect that if our true density itself is close to this shape, then maybe we will get a better accuracy of our estimator. So that is called the adaptive property of the estimator. So we just use the MLE, the same estimator all the way through. And we know that in the worst case, we will get some rate of convergence. But since that our estimator is kind of automatic procedure, when the true density is actually very simple, the MLE doesn't know whether our true density is simple or not beforehand, but automatically MLE, the estimator, shows a better accuracy. That's the definition of adaptive property in this area. Yes, so that's our guess somehow, and we wanted to know whether it's really true in simulation. So before doing a lot of calculations, we always do some simulation, right? So here I generated some sample from 4 different truths. So normal, Laplace, uniform, and exponential. The reason I chose these densities are from this shape, we expect more accuracy when log f0 is close to piecewise affine. So if f0 is like uniform, it means log f0 is one piece. If it's f0 is exponential, we have one piece again. If f0 is double exponential, if we take the log, it has two pieces. So those three kinds are very easy one to estimate for log-concave MLE. That's why we chose those three cases. And in contrast, I also chose a normal case because we expect that normal is quite difficult to be estimated. So we consider these 4 true densities, and we got a sample of size 100, 200, 500, 1000, 1500, and 2000. And then with those samples, I calculated the loss. And here I used the last loss. If you still remember, the x squared is this. The reason is because this loss is largest anyway, so I wanted to control the largest loss. Secondly, the other 3 cases, basically you need to do the integral with your log-concave MLE, which is a function on the real line. It's difficult. You need to know the value of your MLE for the whole interval, but for this last loss, you just need to know the MLE value only at the data point. So when you do the really calculation in a computer, this is very easy to compute. That's why I chose the last loss function. And I iterated the calculation like 30 iterations, because sometimes the results are not very stable. Of course, it's all random. So I took the average of those values and plotted here. The left plot is sample size versus KL at data loss. And we can see that normal is the largest and the other are a bit small. But I also plotted with log of sample size versus log of KL at data loss. It's just because if we think that our risk is like n to the minus alpha rate, then by taking the log of sample and log of the rate, basically this slope should be equal to minus slope, so minus alpha. This slope should be, more or less similar to minus alpha. So what I wanted to see from this plot is actually for Laplace uniform exponential case, somehow this slope itself is close to minus 1. And normal case, maybe it's larger than that. That's what I wanted to find. And as you can see, these three cases, so the maximum is like minus, I don't know, like minus 3 point something, and the minimum is minus 6 point something, so it's like 3, and this part is 4.5, 7.5, it's 3. So basically this slope is minus 1, which is what I wanted to show, because I wanted to show that this simple case has a convergence rate 1 over n. This is much faster than n to the minus 4/5, which is the minimax optimal rate for the one-dimensional case. So from simulation, okay, we have had some intuition and seems it's okay, so we go on. But this type of adaptive property is quite universal phenomenon in the shape constraint area. So for the non-increasing density, I talked about Grenander in the almost the first slide, and Bilger proved the adaptive property of Grenander estimator in 1989, and then after that, people have considered other estimators and adaptive property for the multivariate cases as well. So this is a non-increasing shape, and for the convex shape, convex regression case, also there are some adaptive results. In log-concave density estimation case, Barrow and Bilger proved some adaptive property, but with a different estimator. And this estimator, as far as I know, this is quite difficult to calculate. So we wanted to prove some adaptive result for the log-concave MLE, which is computable. So how can we prove this adaptive result? We saw two different strategies. The first one is Marshall's inequality. This relates this quantity and the other quantity that I'm going to explain later. So this is our first strategy, and the second strategy is empirical process theory by considering complexity of the parameter space. So let's look at our first strategy first. So with this strategy, we found a very interesting result. So suppose our density was actually uniform 0, 1. Then what we found is that the total variation distance between f and head and the truth is again much smaller than n to the minus 2/5. So this is also minimax optimal rate because there's a squared part is missing. So this is basically total variation squared is like n to the minus 4/5. So this is much smaller than our minimax optimal rate in expectation. Specifically, we found that this total variation risk can be upper bounded by n to the minus half, which is again the parametric rate. And the constant is also very nice in this case. So how do we prove such result? I just provided some outline here. So when F0 is uniform, it's not difficult to show that the total variation distance is at most 2 times supremum between the cumulative distribution function of our MLE minus CDF of our true density. This is really not very difficult. If you think about it, this F0, if you take the log, that's a 0. And Fn hat, if you take the log, that's a concave function. So basically you are comparing some concave function with 0 basically. And those two are density. So what I'm saying is this. Can everyone see this? So we need to calculate this one, which is the L1 norm. And we know that F0, if you take the log, it's just constant 0, if it's a uniform. And if you take the log, that is a concave function, right? And there must be some reason where this Fn hat is larger than F0 because they are density, they must integrate up to 1. So with this is a log scale. In the density scale, F0 is again 0, and Fn hat, it should be a little bit different from this, but anyway, we need to have some interval where Fn hat is larger than F0. That's clear, right? So let's say this point is S and this point is T. That is equal to S to T Fn hat minus F0 with twice. Because that integral and this integral must be equal. And then basically this is equal to this. There you have your cumulative distribution function minus right, and then we can compare this guy and that guy, so that we have, okay, I forgot this half factor. So sometimes people define total variation with half or without half, but in my slide there was half, so actually there is no 2 here. So this is supremum over Fn x minus F0 x, and because there are 2 terms, and we just upper bounded with it, absolutely. And that's the definition of L infinity. Okay, so in this special case of F0, it's like this easy to bound the total variation distance with 2 times L infinity norm. Okay, so it's okay to show the first part, and then we assume this scenario. If this quantity can be replaced by that quantity, which is a supremum distance between empirical CDF and the true CDF, then we'll be okay, because this guy can be upper bounded by n to the minus half with famous Dvoretzky-Kiefer-Wolfowitz inequality. We all know that the empirical distribution and the true distribution are very close to each other. So that's why it's important to prove Marshall's inequality for log-concave estimation, since Marshall's inequalities relate these two quantities. The original Marshall's inequality was proved for the case where F0 is non-increasing density. So this inequality is just like this, very simple. So everything was written here in G because we, in this case, it is G0 is non-increasing density, and capital G0 is true non-decreasing distribution function, and Gn head is the CDF of MLE, which is Grenander estimator, and double bar Gn is the empirical CDF of the data. So this is original Marshall, and our question is, can we prove this similar inequality for log-concave density estimation? There was some negative result. So the same question actually has been asked in Dungen and Fibak, and then what they showed is we can always construct counterexamples showing that this inequality is not true, even if the right side is multiplied with any fixed constant. That's what they found. So no matter which constant we use, that cannot be upper bounded by this guy. That's what Dungen and Fibak proved. But since this is kind of universal result, they are saying this is also worst case scenario, right? So it's possible that we can find some smaller class of densities which satisfies these relations. And that's what we proved in our paper. So for some specific F0, whose shape is like this is weird at first, e to the alpha 0 times x times some concave function. So for this type of density, at least we have Marshall's inequality. But with the multiplicative vector rho here, okay. Seems strange, but actually this F0 actually contains uniform, say when alpha 0 is 0 and h0 is indicator function, then f0 is uniform. So in that case, kappa is again 0 because alpha 0 is 0, meaning rho can be upper bounded by 3 because kappa is like 0. So 3 and 0 maximum is 3. So we have Marshall's inequality at least for the uniform. This case also includes exponential case as well. Alpha 0 is minus 1. If alpha 0 is minus 1 and h0 is again 1 constant function, then kappa is minus the range of our order statistic. So that is not bounded, of course, but in probability, with high probability, kappa can be upper bounded by log n. So we have this inequality with some log factor. So using these types of ideas, we had our first adaptation result in total variation distance. We proved that the total variation risk can be upper bounded by the summation of these three terms, and then we can take the infimum. So let's look at this second and the third term. So this is total variation distance between our true density with some density in the class of log of phi. So this term can be understood as some approximation term. So as long as our true density is close to one density in this class, then this term will be small. And that term, Kolmogorov-Smirnov, is not Kim and Samworth. Yeah. This term is can be also understood as the approximation term with f and f0. So if our true density is, if our true density is actually in the class of log affine thing, then those two terms are exactly 0. So these are just approximation terms because there's an infimum over here. Yeah, so this implies that when our density is in the class of log affine density, so if we take log of our density, if that's that's a affine function, then total variation risk can be bounded by n to the minus half with log vector. And using this kind of idea, we were able to prove that when f0 is uniform, the constant here is much better. It's like 4. So okay, it was very successful. By using Marshall's inequality, we were able to prove some parametric rate of convergence for some density. But there are two issues here. The first one is we only consider the smallest loss function with an upper bound. That doesn't guarantee us to have an upper bound for the other three loss functions. So this is not good. That's one thing. Another thing is this class, log1 affine, seems too simple to us. At least we wanted to consider the class of log-k affine. At least I wanted to consider piecewise affine functions that's more complex, looking more complex than at least log1 affine, which is just uniform and exponential. That was, yeah, our motivation to go to different directions. So our second approach is this empirical process theory, and this is really used a lot in this field constraint area. Since it's known that we can bound the last loss, the largest loss, via calculating the Hellinger bracketing entropy numbers. These Hellinger bracketing entropy numbers characterizes the complexity of our parameter space. So if these numbers are huge, then our parameter space is quite complex. If these numbers are small, then it means our parameter space is quite simple. So if parameter space is like small, this number is small, then we will have a faster rate of convergence. If these numbers are really huge, it means our space is quite complicated, so the convergence rate will be slow. That's some vague ideas. And what we found is that these numbers can be much smaller if our true density is uniform or exponential compared to the case when f0 is Gaussian. So I'm not sure if all of you are familiar with this complexity number, so I wrote down some formal definition of bracketing number here. So when I say Hellinger bracketing number, we usually denote it by capital N, since this is a number, and bracketing number, and we are using capital N's of bracket. This is called bracket, right? And then we need three different elements here. The first element is the space that we want to cover. So I said the space is complex or simple, that space we need. The second one is the separation level, epsilon. And third element, we need a distance function. So this number is the smallest integer for which there exist these pairs of functions. So the smallest integer capital N, such that we have capital N number of pairs of functions, where these pairs are epsilon Hellinger distance apart at most, and for every density f in the class that we want to cover, there exists the index J star such that the density is sandwiched between the upper and the lower pair. So we say this f is bracketed between these two functions. These Hellinger bracketing functions can be understood as also the number of partitions, such that all the functions in here, so this curly f is our parameter space to cover, and all the functions in here can be represented as one bracketing function, because these functions will be upper bounded by that one and lower bounded by that one, and these two are close enough. And all the other functions here can be upper bounded by fjU and lower bounded by fjL, and these two functions are close enough. So this bracketing number characterizes the complexity of our parameter space. And I told you that we can control this risk by bounding the entropy number for this class. So our curly f here is equal to that guy. So we don't need to consider any log-concave density function, but we only need to consider a log-concave density functions near our true density f0. So in my previous work with Richard, we proved that the class of log-concave densities with mean and variance restrictions, the Hellinger bracketing number is like something. That's what we proved before. But if we restrict our class of densities near f0, when f0 is quite simple, then actually we can prove that this number is much smaller than just global entropy numbers. So in a picture, I tried to somehow show that the complexity of the whole region is quite complex, but near f0, we only need this partition. It's too vague, but still, So we let log of x0 be affine, and what we proved is that this Hellinger bracketing number for the class where the densities are near f0 within delta Hellinger distance, this guy is much smaller than just global entropy numbers. This was obtained in the previous paper. More precisely, we proved that the log bracketing number, so we say if we take the log bracketing number is it's equal to bracketing entropy. So that's not the different definition. Bracketing entropy is just equal to log of bracketing number. So log bracketing number, bracketing entropy is upper bounded by delta of epsilon to the half power up to log vector. And that gives us basically 1 on n rate. From here to there, you can refer to many books, Sarah van der Geer's book, John Werner's book, and that involves with a lot of empirical process theory. But in the end, all the calculations are kind of getting the log bracketing number. So once we have bracketing number result, we will get the convergence rate of the MLE. That's the result of empirical process theory. So this rate is much faster than n to the minus 4 bits for the minimax upper bound. and also lower bound. So we say that Fn hat adapts to the true density well in this case. And this approach has another merit because we can extend the result to the log k piecewise affine pretty straightforwardly. So we proved that when f0 is close to log k piecewise affine, so this is again the approximation term, then basically we can get the risk upper bounded by k over n up to log factor. So again, if our density itself is exactly equal to log k piecewise affine, the second term is exactly 0, so that we can have only one first term. So this converges to f0 very fast. This is, so as long as our k is some small constant, this rate is 1 on n with log n factor, and that's much faster than n to the minus 4 bits. That's what we proved. So these are some contributions of our univariate adaptation result. And our ongoing work is about whether we can get the adaptive result for the multivariate case. You may think that maybe multivariate case is similar to the univariate case, but actually it's much more difficult since this adaptation will depend on the support as well as log affine shape. So think about two-dimensional log-concave densities. Its support can be anything, right? It could be box or ball, it can be R2, whatever. And support, and then there is a reason why we need to really think carefully about support. So for instance, suppose our f0 is uniform on the ball. So uniform density is log 1 affine, of course. It's very simple. But if it's defined on the ball, this support is very complex. You can think of that way. Then basically we can get the lower bound with Hellinger risk as n to the minus 2 over d plus 1. That is minimax upper bound. So that means even if this is quite simple shape, so this is log 1 affine shape, but if this is defined on the complex domain, then basically we don't have any adaptation because this is equal to minimax upper bound. And from here to there, it's not very difficult. So let's think about a little bit. So dh squared is integral squared fn hat minus squared f0, right? And if we only think about the area complement of our convex hull, then this integral is smaller than the whole integral. So left-hand side is larger than the right side. And then what we know is the log-concave MLE is outside, so the MLE is 0 outside of our convex hull of data. Meaning that the first term on C and complement is just 0, right? So this is the expected value of integral f0 on C and complement. And let's say this ball has unique, the measures 1. Suppose this area is measure 1, so that the density value is like 1 here. Then this is integral C and C, d mu d. That's all, right? Back measure. Then that part is just 1 minus the back measure of Cn. So this is just the outside of the convex hull area. And by Barani and Larman, they proved that this part, outside of the convex hull of the data, that can be, and since f0 is uniform, this is again the back measure, that can be lower bounded by n to the minus 2 over d plus 1. Yeah, so this is why this problem can be much complicated because we need to think of what type of support and also what type of shape will determine these adaptive properties. We need to figure out that. So since we know that uniform on the ball wouldn't work, we just think of the simplest case first, which is uniform on the box. Yeah, this is a contour plot of our log-concave MLE for two-dimensional case. And you can see that when the true density is uniform on the box, yeah, since this is much easy to estimate compared to these two, because there are a lot of wiggleness for the support part if the true is the uniform on the ball and true is the normal part. Since this is the easiest case. And again, in this case, we did some simulation, of course. So it's almost the same scenario with different truths. We considered uniform on the ball because we know that this is the most difficult case in the first place. And we tried the normal because normal is what people are doing all the time. So we wanted to know how our MLE behaves when the true is normal density. And we considered uniform on the box and exponential, and we believe these two are the easiest case. And I plot the similar plot as before. Again, the slope of this line will suggest the convergence rate. And again, we can see that for the uniform on the box and exponential, they gave us the steepest slope, which is quite close to -1, I guess. I mean, it might not be true, but still, as long as this plot is, according to this plot, uniform on the ball, definitely the slope is the largest compared to those two. For the three-dimensional case, similar phenomenon happens again. Those two are steepest slope compared to uniform on the ball. But somehow, interestingly, I found that normal case is kind of in the middle. So we are not sure yet, but maybe there is some possibility of proving adaptive result for normal case. And that will be a bit different from our previous thought because normal is not low piecewise affine. Okay, so this is simulation, and we are convinced that we can get something better for this uniform case. So we tried to obtain the bracketing number when F0 is uniform on the box. So again, we need to calculate local Hellinger bracketing number. And then we believe that when delta is small enough, we can prove the local bracketing number is much smaller than the global bracketing number. So this number was obtained in 2016 paper for dimension up to 3. And we think that this one is kind of this shape. So we believe that log bracketing number is about epsilon over delta to the power minus d minus 1, which gives us again parametric rate. But this is not completely written yet. So we are working on this writing right now. And if this is true, at least we found a true density which gives us really good adaptive property. And this is much faster than our minimax optimal rate, which is n to the minus 2 over d plus 1, when dimension is equal to 2 and 3. So this is ongoing work, and now we need to we are thinking for the case when the true density is some log k piecewise affine, where the support is a polytope with some bounded vertices. Yeah, other than this, we also obtained some more results when the dimension is more than or equal to 4. So I think I only have like 4 minutes, so I'll skip most of it, but I'll just talk about conclusions. And we believe that when dimension is more than or equal to 4, we can get the supreme risk as equal of n to the minus 1 over d minus 1 times the ceiling d over 2. This is quite complicated. What I can say is, before we didn't have any result, any convergence result when d is more than or equal to 4, but now I think we are able to get some rate for this really high dimension, but we are not sure if this is the optimal rate. Of course, this is different from our minimax lower bound, which is n to the minus d over d plus 1. This is lower bound we obtained. That's definitely larger than this. So yeah, we are not completely convinced whether this is the optimal rate or this is the optimal rate. So that's the future work that we need to work with. And we are doing, so now we consider more optimal Franking number calculation. So I only presented for the higher dimensional case when the true is 0, 1 to the d, the box case. But there are so many different cases. We need to be able to think a little bit more about various kinds. And then also, we want to extend our result to more general piecewise affine case. I only consider the uniform right now. That's too simple. And thirdly, I was wondering if the true density is like normal. Is there any adaptive property of log-concave? That's, I think that's an interesting question as well. So this is the main paper that I was talking about, and this is going to appear at Annals, and 2016 paper is here. And thank you very much for your attention.